Hello, physics fans. Welcome back. This is Physics 11. This is about Lesson 5 in the Forces chapter. We're now going to be talking about individual forces and what makes them up, and or at least how to calculate them. First one, gravity. It's a weighty subject. This is one of the forces we've been using all along as things have always been falling down. We've had a whole lesson on falling in kinematics. So, at least we've been using the acceleration due to gravity quite a bit. Here's a formula to calculate the force of gravity. Force is equal to m, which is the mass in kilograms, times g, which we call now the gravitational field strength. You'll notice that the units is kilograms, then times by newtons per kilogram. We'll end up with newtons. Okay. The little g is the exact same little g that we've been using in kinematics as 9.8 meters per second squared. In fact, you can switch back and forth between this unit, which is acceleration, and that, which is gravitational field strength. Same thing. This one is for kinematics, and this one's for dynamics that we're in. Force of gravity has another name, weight. We'll get down to about that down below as we get there, but that's a challenging term because we messed this up in English. Force of gravity, Fg equals mg. What is the force of gravity on a 4.5 kilogram block? Force of gravity is equal to mg, which is 4.5 kg times 9.8 newtons per kg. Even if you wrote down meters per second squared here, it would be fine. Pull up Mr. Calculator. Ooh, big calculator this time. And we go 4.5 times 9.8, and we get 441. Okay, so the force of gravity on this 4.5 kilogram mass object is 441 newtons. So that's the force of gravity. That's its weight. That's how much it weighs. It's 441 newtons. What is the mass of an object that is pulled down by the force of gravity of 167 newtons at the Earth's surface? So, force of gravity is equal to mg. So the force of gravity is 167 newtons. Is equal to m, which is what we're trying to find out. And at the Earth's surface, it's 9.8 newtons per kilogram. So we take the 167. 160. Let's try this one more time here with a different cursor. 167, and we divide that by 9.8, and we get m is 17.04 kg. Number 3, the force of gravity on a 215 kilogram spacecraft on the moon is 409 newtons. What's the gravitational field strength there? So force of gravity is equal to mg. This time I'm just going to rearrange it. G is going to be force of gravity over m. So that's going to be 408 newtons divided by mass is 250 kg, and we get 408 divided by 250. Divided by didn't work. Okay, divided by 1.632 newtons per kilogram. So that's the gravitational field strength on the moon. Oh, by the way, if you dropped an object and you were standing on the moon, how fast would it accelerate towards the ground? 1.632 meters per second squared. Good, that's how fast it would accelerate. Okay, what's the difference between weight and mass, and how is it confused on how everyday society uses these terms? When are weight and mass the same? Okay, first of all, weight and mass are not the same. Weight is the force of gravity, and mass is the kilograms. Mass is talking about all the protons that make this up, and you add up all the protons and all the neutrons and all that stuff, and that doesn't change. The mass doesn't change of an object, no matter where you put it in the universe. The mass doesn't change, but the force of gravity changes. You put it way out in space, away from everything else, that's practically zero. You put it on Jupiter, and that's going to be a lot. And on the Earth, you multiply this by that. So they're two different things. Okay, so when are they the same? They aren't. Now, the numbers might be the same. If G was 1, then 10 kilograms would have a force of gravity of 10 newtons. But is 10 kilograms the same thing as 10 newtons? No. Okay? And now how do we get these mixed up, right? How much does something weigh? We're asking about what is the force of gravity acting upon it. Yet we always answer in mass. We answer like, it's so many kilograms or so many pounds. Kilograms and pounds are mass. So when we ask for something, how much does it weigh, we're actually asking, what is the object's mass? So this is where society messes it up. Because when we answer in weight, someone says, how much do you weigh? Are you asking for it in newtons? Okay, 800 newtons. Whatever. Okay. So what is weight? Weight is a force. And it's the force of gravity acting on a mass. Okay, so without watching me, get these next 6 done. Zip, 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 zip. Okay, pause it. 10, 9, 8, 7, 6. Pause, please. 5, 4, 3, 2, 1. Well, welcome back. Right? You've paused. Good. 5 kilogram block. What is the force of gravitational force on it? The magnitude, the size of it? It's 49 newtons. Number 2. What is the direction of number 1? Did you answer towards the center of the Earth? That's correct. If you said down, well, this towards the center of the Earth is labeled as down. Okay? But out in space, which way is down? What is the gravitational force on a quarter pounder? 2.2 pounds equals 1 kilogram. So what is the gravitational force on a quarter pounder? Have you done it? Have you done the calculation? Pause it. 3, 2, 1. I know you didn't pause it. You just kept on playing. Here we go. The mass, first of all, we have to get the mass of it. It's in 0.25 pounds, but we have to convert it. So it's 1 kilogram is 22.2 pounds. So to that conversion, we get that the mass of a quarter pounder is 0.1136 kilograms. Force of gravity equals mg. Put the number we just got, 9.8. It's 1.11 newtons. Now it's going to be less because of the fat coming out, so it's going to be closer to 1 newton. Therefore, a quarter pounder can actually be called a Newton burger. Number 4. Do this ahead of me, please. How much does a 125 Newton bicycle weigh? Did you calculate it? Pause it. Okay, did you get tricked into it? It's 125 newtons. Because weigh is weight, and that's the force of gravity. And the force of gravity is measured in newtons, and it's already there. That's the trick in English. People are going to convert it to mass. I'm not asking what's the mass of a 125 Newton bicycle, because then you can do the calculation. On Mars, where the gravitational field strength is now a little bit different, 3.73 newtons per kilogram, what is the weight of a 5 kilogram block? It's 5 kilograms, isn't it? 5 kilograms. No. Weight is the force of gravity. So force of gravity is equal to mg. Do it out. Okay, and number 6. Figure it out. 3, 2. Okay, here we go. Whoops, it's going. There we go. So the 5 kilogram object on Mars has about 18.65 newtons. On Earth, 49. So it weighs more on the Earth. If the gravitational force is 60 newtons, what's the object's mass? Mass is just going to be 6.122. Let's talk about this now. Clarity. If someone stands on a scale, what the scale reads is called weighs or weigh, and is the normal force. So you're standing on a scale, and it's pushing up on you because you're pushing down on it. You're pushing down on there with your force of gravity, and this is pushing back on you with the normal force. And usually when you're standing on the scale, you're not zooming up or going down. So these have to balance. And this is called how much you weigh, or something weighs so much. It's the normal force. Your weight is the force of gravity pulling down on you, and that doesn't change. Unless, of course, you lose mass, or you move away from the Earth, your force of gravity doesn't change on you. By the way, Weight Watchers should not be called Weight Watchers. It should be called Mass Watchers. Weight Watchers, you could lose almost all your weight just going into space. Woo! I lost weight today. How much did you lose? All of it. I went into deep space. What? You only lose mass by, shedding some of the protons and neutrons and electrons that you have in your body. Sweating, exercising and burning it. Okay, so when you are at rest and you're on a scale, the upward normal force equals the downward force of gravity. So when you're at rest on a scale, what the scale reads is equal to your weight. Weight is force of gravity. So there's a T there. How much it weighs, or if you're weighing something, that's this normal force pulling back on you. But the scale doesn't always show your weight. The scale doesn't always show your weight. This is your weight, and this is the scale. Why aren't they always equal? That means that if they're not equal, what happens if you sat on a roller coaster? Or if you jumped off a chair onto the scale? It would show a lot higher than your weight. What if you stood on the scale in space? Well, if you're floating around in space and put that underneath your feet, if you're floating around and you try to attach, it would show 0 because you're not pushing down on it. Your weight is not pushing on it. Your force of gravity is not pulling. So it's not. It shows you that you're weightless. But are you really weightless? Yes, the force of gravity is 0, but you're not massless. Okay, let's just do one question here. You haven't seen it yet. This is the first time you're seeing it. A 5 kilogram mass is being pulled by a rope, and it's been pulled up. So here's our mass, and it's being pulled up by a rope. There's a little hook on the top there, and then there's a rope tied around it, and it's being pulled up. And there's a tension force in here of 79 newtons, and this is 5 kilograms. And they say it's being pulled up, so I guess the direction is up. how much time would it take to lift 48 meters? Okay, so 48 meters, and we want to know the time. Okay, first draw your free body diagram. Didn't I just do it? No, you didn't. Close. Tension, force of gravity. There's your free body diagram. Don't draw anything else in there. Free body diagram. And the tension, we're told, is, notice it's on the outside of the box, 79 newtons. And the force of gravity is equal to mg, which is equal to 5 times 9.8. So this is equal to 49 newtons. Okay, so now that we do this, we have to start off with Newton's second law. Once it starts to get into calculations, more than just throwing it to mg formula, we write down Newton's second law, which is the sum of the forces equals F net, which equals ma. That's your first step. Then you look at the free body diagram, and since it's going up, this is winning and that's losing. So you take winning, subtract losing. So force of gravity minus tension is equal to ma. Please, you need that. That's going to be probably one of the most important lines to get marks. If you're going to show your work, that's what you need to do. And then the force of gravity is... Oh, what? Mr. Curl made a mistake. Here he goes. Force of gravity is not winning. Tension's winning. Take out my eraser. Okay, yes, I could back it up and delete it, but it's good to see. Tension minus the force of gravity, winning subtract losing, equals ma. And that's what I'm going to look for, for marks. And so the tension is 79 newtons minus 49 newtons is equal to the mass 5 times A. This is 30 newtons, because that was newtons. And that equals 5 kilograms times A. So A is going to equal 6 meters per second squared. And how much time from rest? So the initial speed is 0. The acceleration we just calculated is 6 meters per second squared, and that's up because it's always in the direction of the winning. And the distance that we have to go is 48 meters. How much time does it take to lift? Time. So we're going to use D equals BIT plus 1/2 AT squared. This is going to be 0 because that's 0. So time is going to equal the square root of 2D over A. And we plug these numbers in. And 2D is 2 times 48 divided by 6, all square rooted. So 48 divided by 6 is 8. 2 times 8 is 16. Square root of 16 is 4 seconds. That's the answer. Okay, how to solve it. Kind of picture what's going on. Draw a free body diagram. No numbers inside, just arrows. Put numbers that you can outside, direction stuff. Newton's second law. How does it apply to this question? Plug the numbers in and solve. And this time I had to get the dynamics done, and then I had to go to kinematics to solve the rest. Yay, thanks for paying attention. Enjoy.